Okay, so let's start the class, and we have done the 1D Crank-Nicolson Fdtd in the last class, and today we'll do the 2D case. 2D case, 3D case I will not be doing. If you are interested, I will give you some material to study because that will be too much for you. We have another Fdtd after this, so that also I'll start discussing today. So CN Fdtd is an unconditionally stable Fdtd, and it can give you faster Fdtd program. So let's consider 2D case. 2D case, let's say if you consider TZ case. TZ means electric field doesn't have any component along the Z direction. So EZ is 0. In that case, electric field can have EX and EY component. And electric field and magnetic field, most of the time we consider perpendicular to each other. So we can have only a Z component of the magnetic field. So these are the three Maxwell equations for the 2D Fdtd for the TZ case. So we want to solve this using the CN Fdtd, Crank-Nicolson Fdtd, which is a unconditionally stable Fdtd. So in the conventional Fdtd, so if I want to discretize this, you already know how to do the discretization for this. What do? I actually find EX at n plus 1, then I need to use IZ at n plus half. So I actually find the EX at n plus 1 from the EX at previous time instant and the IZ at the previous time instant of the neighboring cells. That was the idea. So that's a conventional Fdtd. In the conventional Fdtd, we always find the present time electric field from the previous time value of the electric field as well as the previous time value of the magnetic field of the neighboring cells. So that's a conventional Fdtd. But in the implicit, this is called explicit Fdtd. And in the implicit Fdtd, which are actually unconditionally stable, let us try to see how do we find this update equation. So we have this here, IZ at n plus 1, IZ at n plus 1. In the CN Fdtd, what do we do with these terms? So let's see. Okay, this is the equation we want to solve using Fdtd, and the conventional Fdtd have this. So, and we have this extra term here, IZ at n plus, we have this term here, not extra term, IZ at n plus 1, IZ at n plus 1. So this IZ at n plus 1, if we want to apply CN Fdtd, which is the unconditionally stable Fdtd, then we actually normalize IZ at n plus 1 and IZ at n. So we normalize it. That means we take average of IZ at n plus 1 and IZ at n. So this term IZ at n plus 1 half is replaced by IZ at n plus 1 plus IZ at n divided by 2. Similarly, this term here, IZ at n plus half, will be taken average of the IZ at n plus 1 and IZ at n plus 1 n. So when we do that, we already have an implicit term here, IZ at n plus 1, IZ at n plus 1 in the right hand side. We want to find a left hand side term, but in the right hand side we have the implicit terms here, IZ at n plus 1, IZ at n plus 1. So that's the whole idea of the implicit Fdtd, but then you will ultimately replace this by using one of the Maxwell equations. And again, let's look at the second equation for the 2D Fdtd. Fdtd, we have this dou Ey by dou t is equal to minus 1 by epsilon dou Iz by dou x. So in the conventional Fdtd, if I want to find Ey at n plus 1, then I find Ey at nth time instant, then the Iz at n plus half and Iz at n plus half. And this space location, you already know what to do because this is a time del by del x. So Iz would be calculated at I plus half, J plus half, I minus half. So this is the derivative with respect to x. So I should have I minus half here. I should have J plus half here. I should not change this. There are some typos here. Anyway, if you know how to do it, you don't need to worry about all these typos. You can do it on your own also. Okay, so the idea is this term here, Iz at n plus half, Iz at n plus half. What do I do with CN Fdtd? So this is the equation I want to discretize, and this is a conventional one. So I replace this Iz at n plus 1 half by Iz at average of Iz at n plus 1 and Iz at n. And again, this second term also I have Iz at n plus half. I will replace it by average of Iz at n plus 1 and Iz at n. with the average. So obviously because of that we have implicit term in the right hand side is iz at n plus 1 because we are calculating EUI at n plus 1, but we need the value of iz at n plus 1. Again, we have one more equation. So this is the third equation for the 2D FDTD. Conventional case, you know it. If I want to find iz at n plus 1, then I use the value of iz at n and ex at n plus half. I use that previous value of the electric field and magnetic field. So if I want to find electric field at n plus 1, I use the previous value of if I want to find the magnetic field iz at n plus 1, I use the previous value of iz at n. Then I actually also use the value of electric field at n plus half of the neighboring shells. So now the problem is that I want to get rid of this ex at n plus half, ex at n plus half. So ex plus n plus half, I can replace it by taking average of ex at n plus 1 and ex at n for this same location. Then again, if I want to find ex at n plus half for the same location, I take the average of ex at n plus 1 and ex at n. Similarly, this term also I'll take average of ey at n plus 1 and ey at n times 10. Similarly, here also I'll do that. Location is still the same. So this is how you do the CN FDTD. That's the whole process. So now you have this equation 1, 2, and 3. I'll call this first equation as equation 1. So your equation 1 for the CN FDTD. This is your equation 2 of the CN FDTD. This is the equation 3 of your CN FDTD. So I have 1, 2, 3 equations. So I can use substitute equation 1 and 2 in equation 3. And if you do that, so if you substitute equation 1 and 2 in equation 3, then you would be able to get the updated equation for the iz at n plus 1. So if you want to get the iz at n plus 1, then you substitute equation 1 and 2 into equation 3. So this is the final equation 1 minus b square d2x n plus 1 plus d2y n plus 1. iz at n plus 1 at I plus half j plus half. What is b? B is a constant, c delta t by 2. What is d2x? d2x means double derivative with respect to x. So d2x means double derivative with respect to x. So we are actually doing double derivative with respect to x. So there is a delta x square here. What are we doing? We are actually doing the double derivative of with respect to x of iz at n plus 1. So iz at n plus 1 we are doing, that's why we have n plus 1 here. So here again we are doing double derivative with respect to y at n plus 1. So d2y is double derivative delta y square, and it is done at n plus 1 times. Then you can also in the right hand side what we have is 1 plus b square d2x n plus d2y, same expression except that this n here times 10. In the left hand side is n plus 1, it is n here. So what you can see is the right hand side, all the terms are dependent at the nth times 10. Left hand side, all the terms are dependent on the n plus 1 times 10. So from here we can find out what is the updated equation for the magnetic field at the n plus 1 times 10. Okay, so these are the double derivatives. So you know what is double derivatives now. If I want to do double derivatives, so iz at n plus 1 with respect to x, we are doing double derivative. So I have I plus 3 by 2, I minus 3 by I plus 3 by 2, then twice of I plus half, then I minus half. So double derivative, no? So delta x square. So this is the double derivative with respect to x. If this double derivative with respect to y, you have delta y square in the denominator. And now you are doing double derivative with respect to y. So iz at j plus 3 by 2 minus 2, j plus half, then j minus half. That's how you do the double derivative. And this function here is dependent on ex at n at times 10 and ey at times 10. This is the equation you have here for this function here. So that's a compact notation. So with this equation, you can actually do the update equation for the magnetic field. Similarly, you can also do it for the electric field, 2 electric fields. So you can explore. So this is about the 2D FDTD. If you are interested in 3D CN FDTD, so when I introduced this to the class, I think 2 years back, 2 or 1 year back, 1 year. So 1 or 2 years back, so I have been taking this course from the starting of your RF photonics program. So first time when I introduced it, that time 3D FDTD was not available in the literature, but now I think it's available in the literature. Recently, there's a paper here. So if you're interested in 3D and FDTD, you can explore this paper. So we'll not discuss this in this class. We have another FDTD, which is very much important, especially for modeling different kind of metamaterials or any kind of medium. Nowadays, you have a lot of artificial mediums which has very good properties, which cannot be realized with the naturally occurring materials. So those kind of medium, it's very easy to model using another type of FDTD, which is called auxiliary differential equation FDTD, ADE FDTD. So depending on what kind of material you're considering, you'll have different other equation for the FDTD. So this is one of the very popular FDTD for modeling different kind of medium material. No? We have different kind of material models are there. Based on that, we can develop something called ADE FDTD. I have briefly discussed about this auxiliary differential equation FDTD in one of your previous classes, where we introduce an auxiliary function and do the FDTD of that equation. So that is very similar to that, but then here we'll try to model it for different kind of materials. For example, let us try to analyze, we'll do a quick digression here because you need to know something about the material model also in order to understand this ADE FDTD. So I'll just give you a brief background on the different material model we have. The most generally used material model is the Lorentz model. Lorentz model is the most general model. From there you can take particular cases like Debye or all those kind of models later on. So in the Lorentz model of the material, your electron motion is described in terms of driven damped harmonic oscillator. So it's basically they actually model it as a harmonic oscillator which has been damped and it is driven by some electric field. We'll see that in the next slide. And we also assume that charges are allowed to move in the same direction as the electric field. So the model will be very clear from this here. So in the Lorentz model, we describe the temporal response of the component of the electric polarization field. So we are applying some electric field to a medium. There will be a polarization field generated inside the medium. So we actually model the polarization field inside the medium from the incident or applied electric field we're applying to the medium. So let's say there's a medium, you just apply some electric field. What is the polarization field inside the medium? That is given by the Lorentz model. In the Lorentz model, we actually describe the temporal time response of the component of the polarization of field of the medium to the same component of the electric field. So let's say this is Ex, then we are considering Px, Ey, then Py, Ez, then Pz. So same component of the polarization field and the electric field. Incident electric field is what we are applying to the medium. Polarization field is what is the field which is existing in the medium. So this model is very general, and from there we can take particular cases later on. So look at the first term here. You have a double derivative. That means basically this is the acceleration of charge. Second term here you have a single derivative, and this is basically due to damping mechanism of the system with the damping coefficient gamma L. So we call this gamma L as damping coefficient, and L is because subscript L is for Lorentz model. We'll later on see Debye or any other model, then we'll change this L to D. That's why I'm just clearly stating from the beginning. L means here is the for the Lorentz model. Gamma is the damping coefficient. So this portion will damp the oscillation. Which portion will give you the oscillation? Oscillation is given by the third portion here. Third portion here is omega naught square pi here. So this is a restoring process with characteristics frequency f naught is equal to omega naught by 2 pi. So we have three terms here. One is acceleration, one is speed, and this is oscillation. And what are we supplying to the medium? We are supplying electric field of Ei, and this chi L is called the coupling coefficient for the Lorentz model. Epsilon 0 is the electric permittivity for free space. So this is a model, Lorentz model for the polarization field with respect to the electric field which is applied to the medium. So this model is very simple. You have double differentiation, single differentiation, no differentiation. Then you are applying something here that is in the right hand side. Chi L is the coupling coefficient. Okay, so this is the model we have here. This is in the time domain. If I want to convert into space domain, if you consider time harmonic fields, then all the del by del t terms will be replaced by j omega. So del square by del t will become minus omega square, and del by del t will become j omega. We don't have any differentiation here. So in the frequency domain, I can write this pi omega. Omega is the frequency dependent time angular frequency. Pi omega is what you have in the right hand side, epsilon 0 ei omega into chi L. Chi L is the coupling coefficient for the Lorentz model. So we have epsilon 0 ei omega chi L divided by this differentiation, double differentiation will become minus omega square, gamma L into j omega, this will become, and this will become simply omega naught square. So this is in the frequency domain. But if we have small losses, if you have very small losses, this damping coefficient is actually considering the losses taken into account. If we have very small value of these losses, gamma L by omega naught is very much less than 1, then this term is 0, then you can clearly see that this is resonating at frequency of f naught or angular frequency of omega naught. So this term will become 0 if you have very small losses. So this model is actually oscillating at omega naught, angular frequency or natural frequency of f naught. Okay, so we actually define some material parameters like electric susceptibility. This must, I think you must have learned this even in your +2 also, later on also in the EM theory courses. We define electric susceptibility as ratio of the polarization divided by electric field. So we take the ratio of polarization divided by electric field into epsilon naught, then we get the electric susceptibility. Electric susceptibility will be denoted by chi E. E for electric susceptibility, L for Lorentz. So looking at this expression you have here, Pi by epsilon 0 omega, Pi by epsilon 0 Ei omega would be chi L divided by this term here. So this is what we have here. So the electric susceptibility can be expressed as chi L. Chi L is the coupling coefficient divided by minus omega square plus j gamma L. Gamma L is damping coefficient, omega plus omega naught square. This is the natural resonant frequency. Omega is the frequency at which we are modeling the material or medium. And you know that from your fundamental physics, even at your +2 level or in your undergraduate studies, we can define the epsilon for this medium at omega frequency is epsilon 0 1 plus chi E Lorentz omega. So if I just add epsilon 0 with epsilon 0 into chi E, then I get the value of the epsilon. So as I already told you, Lorentz model is the most general model you have for the medium or the material. There are other models which are called Debye model, Drude model. These are very common. So if you actually do modeling for different kind of medium material, and if you want to do FTD simulation for different medium material, because this artificial mediums are widely used nowadays. You use artificial mediums practically also in simulation also. So we need to have a proper model, proper update equation inside this artificial medium or this kind of medium. So we'll have different kinds. So basically in the Fdtd, you have the same Fdtd program in free space. Then you have different Fdtd program when you are inside the PML medium. You'll have a different Fdtd program if you are inside the artificial medium or any medium which is following this model, Debye model or Drude model or Lorentz model. So at different locations, so that's the only difficulty in the Fdtd. At different solution space, different location, if you have different medium, you will have to have different update equation. If it is in free space, you have the traditional Fdtd update equation. If you are in PML, then you have to use stress coordinate system and write the PML update equation. But if you are inside the Debye model medium, which can be modeled using Debye or Drude model or Lorentz model, you will have to have different Fdtd program update equation inside the medium. So that's why we are doing that, because now there's different mediums are used for different purpose, it will be able to improve the device performance or any kind. For example, device model, in the device model, we actually neglect the acceleration term. Acceleration term was the first term, we just neglect it. So that's a model we have. In the device model, acceleration term is no longer existing. It's not very pronounced, it's very small, so you can neglect it. So you have this here. In the model, so first term is 0, so you have gamma d del by del t pi plus omega 0 square pi is equal to epsilon 0 chi t ei. Okay, so this is the model you have here. First term is 0 from the Lorentz model, then you get the device model. So these are actually proposed by different people. So the name is different because of the person who has originated this kind of models. So in the frequency domain also we'll neglect the first term. So the electric susceptibility for device model at omega frequency is chi d. So I have replaced L by D here because we are in the device model here. So coupling coefficient for device model divided by J gamma, the damping coefficient for the device model omega plus omega naught square. So because of the first term is gone, we also have some changes in the electric susceptibility for device model. So Drude model is different than device model. In the Drude model, we actually neglect the second term. No, not the second term, third term. So the restoring force is negligible. So we neglect the third term. So we have the first and second term here. Because of that, we'll also have some change in the electric permittivity for the Drude model. Drude model, electric permittivity, no. Electric susceptibility for the Drude model is chi L divided by minus omega square plus J gamma D, gamma L, this will be gamma L here, omega. L for the, not L, so this is the Drude model. So gamma D divided by minus omega square plus J gamma D, omega. So L should be replaced by D here because we are in Drude model. And this D is for the Drude model. So gamma D divided by minus omega square plus J gamma D, omega. So gamma D is the coupling coefficient for the Drude model, and chi D is the coupling coefficient for the Drude model. Gamma D is the damping coefficient for the Drude model. So this is how you get the device model and Drude model from the Lorentz models. In the device model, you neglect the first term. In Drude model, you neglect the last term in the left-hand side of the Lorentz model. So what you can observe is that in all these models at high frequency, when frequency is tending to infinity, the permittivity actually reduced to that of the free space. When you go for higher and higher frequency is tending to infinity, the permittivity of the medium always tends to that of the free space. So that is one point you can keep in mind, but usually that is true for the naturally occurring materials. But if you are doing Fdtd simulation, you can take any value. So that's why we actually write it as epsilon infinity. Later on, we'll discuss that. For a linear material, we have the relationship between the electric flux density and electric field. So electric field flux density D is equal to epsilon E. This is a very simple relation. You know it from your fundamentals of electromagnetics. D is equal to epsilon E. So here your epsilon is a complex number. It is dependent on the location as well as the frequency. So here, when I say that dr omega is equal to epsilon r omega, er omega, that means I'm considering at specific location r and frequency omega. So this relation holds true for each value of frequency and the point in the space. So we can write this in a more simplified form. D is equal to epsilon 0 epsilon infinity E plus PR. So this is the usual relation you have between the electric flux density and polarization field and the electric field. So D is equal to epsilon 0 epsilon infinity E plus P. P is the polarization field, E is the field you are applying to the medium, D is the electric flux density. So now you can again simplify this. This is a simple relation you must have understood from your undergraduate studies in electromagnetic field theory. So we can replace this D is equal to epsilon 0 epsilon infinity E plus epsilon 0. This polarization field, we know what's the relation of this polarization field with the electric field. So we just multiply epsilon 0 with the chi e. Chi is the electric susceptibility. You with the electric field, then you get the polarization field. So that's the simplification we are doing here. So P is the polarization phasor. We are in frequency domain. Chi e is the electric susceptibility of the material. Epsilon infinity usually is 1 for all real materials, but in the Fdtd simulation, you can take any kind of medium. So we'll just keep it as epsilon infinity. Otherwise, most of the cases when you consider naturally occurring materials, epsilon infinity is 1. We have another term, epsilon dc, is the relative permittivity at the lower end of the frequency. When frequency omega is tending to 0, how much is the relative permittivity will denote it by epsilon dc. So at the omega is equal to 0, what is the permittivity of the medium? That will be epsilon dc into epsilon 0. This is relative permittivity. Here again, what is the permittivity of the medium at the infinity? Omega tends to infinity. That will be epsilon 0 into epsilon infinity. This is the relative permittivity at the upper end. This is the relative permittivity at the lower end of the frequency. Hence, complex electric permittivity is related to the susceptibility like this. Your epsilon c, complex value of the epsilon, which is the electric permittivity, is equal to epsilon 0, epsilon infinity, epsilon 0, chi. Okay, so how do we come up with this different model for the material is also dependent on what we're going to discuss now. What we're going to discuss now is that what we have here is the relation epsilon c is equal to epsilon 0, epsilon infinity, epsilon 0 into chi e at the frequency omega. So this can be expressed like this. Epsilon c omega is equal to epsilon 0, epsilon infinity. This is a chi is a frequency dependent parameter. So if I know what is the time dependent parameter for the chi e, I just do the Fourier transform of that. I will be getting chi e omega. So if I do Fourier transform of chi e t, then I should be getting chi e omega. So that's what I have done here. So this chi e t is some kind of decay factor. So what kind of function you consider for this chi e t will give you different medium. For example, Debye model, or let's say Lorentz model, or all those models we have considered before. Different model will have different value for the chi e t. So the chi e t here, it will have different function. Based on that, we'll have different model for the medium. So just looking at this chi e t here, what was epsilon c at omega tends to infinity? Omega tends to infinity, epsilon c will become simply epsilon 0 into epsilon infinity. Only the first term will be existing when omega tends to infinity. Epsilon c, omega tends to infinity will be epsilon 0 into epsilon infinity. This term is going to become 0 when omega is tending to infinity. So looking at this, what we actually see is that chi e t should be tending to 0 for omega tending to infinity. Then only this term will become 0. Then at omega tending to infinity, epsilon c omega will be equal to epsilon 0 into epsilon infinity. So what kind of function this can have? So this could be a decaying function, something like this. So we have a Debye model. That is because P. Debye, the famous person who has actually started the Debye model, he gave a very simple exponential model for this decay factor. So his model is chi e t is chi e 0 exponential minus t by t naught ut. So this model is given by P. Debye. So P. Debye has given this model. That's why we call it Debye model. So in the Debye model, chi e t as a function of time is equal to chi e at time is equal to 0 exponential minus t by t naught, where t naught is the Debye relaxation time constant. So this is an exponential decaying function. When t tends to infinity, this will become 0. That's what we wanted also, because epsilon c becomes epsilon 0, epsilon infinity, and this term becomes 0. If I have a function like this term is going to become 0 at t tends to infinity. So let's see. The ut is the unit time step function, the unit step function. Tau naught is the Debye relaxation time constant. So now, what was the equation we have here? Equation we have here is the epsilon c omega is equal to epsilon 0, epsilon infinity plus Fourier transform of epsilon chi e t. So we have the expression for chi e t, just plug it in here, you do the Fourier transform of that, then we get the relation. So when I plug in the value of chi e t, according to the Debye model here, then I will get this equation as 0 to infinity chi naught t. Exponential minus j omega t was already there from the Fourier transform. Then we also have this function here, no? This function here, exponential minus t by tau naught. So I can simply write it in this form here. So looking at this, you can do the integration of this chi naught t. This would be chi naught 0 here. So chi naught 0, let's say is a constant, then you can do the integration of this is an exponential function. What do you get? 1 by tau naught plus 1 j omega. So you do the exponential function integration, you can plug in the value 0 to infinity, you simply get this here. So what we are getting is that in the Debye model, epsilon c omega is equal to epsilon 0, epsilon infinity plus chi e at time t is equal to 0, 1 by tau naught plus j omega. You can further simplify it. Chi e at omega is equal to epsilon 0, epsilon infinity, chi e at 0, tau naught 1 by divided by 1 plus j omega tau naught. So another thing is that at time at the omega is equal to 0, at omega is equal to 0, that means at the DC frequency, when omega is at the lower end, what happens to this relation? So omega at lower end, omega tends to 0, this will become 0, this term will become simply 1. So epsilon c at omega is equal to 0 is epsilon dc into epsilon 0. We have defined epsilon dc like that. This is the relative permittivity of the electric relative permittivity at DC frequency. So epsilon dc into epsilon 0 is equal to, from this relation we have derived epsilon 0 epsilon infinity plus epsilon 0 chi e 0 tau naught. This term will become 1 because omega is tending to 0. This is the relation we have here. So from here I can find out what is chi e at time t is equal to 0. Chi e at 0 is epsilon dc minus epsilon infinity divided by tau naught. So if I substitute this value of epsilon at 0 here in this relation, final expression we have for the chi e for Debye model at frequency omega is epsilon 0, epsilon infinity plus epsilon dc minus epsilon infinity divided by 1 plus j omega tau naught. Okay, I think I should stop here. From there, we'll actually try to do update equation for the Debye model of the material.